In this video, we're going to explore an important idea in studying differential equations that doesn't necessarily require actually solving the differential equation itself. So the solving process can be quite challenging because it involves integration. There are other properties that we can study, though, that do not require going through that full step. Take a look, for example, at this differential equation, dh dt equals minus 0.25 h minus 200. This is our model for a heating and cooling system with an environmental temperature of 200 degrees Celsius, and h being the temperature of some object in that environment. The question we're asking here is, what would the equilibrium temperature or temperatures be of the potato? And redefining equilibrium again, an equilibrium in this case here would be a temperature of the potato for which, if we start at that temperature, we're going to stay there forever. So let's take a look at either the math or the concept in that. Here's the formula for the rate of change of the temperature of the potato, and select one of the options here that makes the most sense to you. Pause the video if you need to, and then we'll check in. The key translation here is that if we start at a certain temperature, we stay at that temperature forever. That implies that h is constant, and that implies that dh dt is going to equal 0. So to find the equilibrium temperature, we simply set dh dt equal to 0. And that gives us here 0 equals minus 0.25 times h minus 200. That's the temperature which will yield a rate of change of 0. And we see pretty quickly that that's h equals 200. So that gives us C as the correct answer. We then check in to make sure that's reasonable in the model, and of course it is. So the potato starts at 200 degrees, then it's at the temperature of the oven. It's not going to change temperature after that. It's at the same temperature as the oven, and it's going to stay at that temperature forever. So the equilibria usually have some interpretation both in the mathematics and in the scenario itself, and they should be complementary to each other. Let's take a look at another couple of examples to reinforce that idea. In this scenario, we're looking at water leaking out of a cylindrical tank. So there's a hole in the bottom here, water's leaking out, and there's going to be a certain depth of water in the tank, and that's going to be defined by a height h. And you can look at some of the forces and the acceleration due to gravity, things like that, and you can come up with an equation that defines the rate of change of h. Notice it's going to be negative because h will be decreasing. If we're talking about water levels in a tank and there's a hole, that's a pretty natural direction for the water level to go. And then we can ask the follow-up question, which is, what is the equilibrium level of water in the tank? If we start at a certain depth of water, what would that water level have to be so that it stays constant forever afterwards? Consider these options here, pause the video, and then we'll check our answers. Okay, same idea as the last case. We're looking for an h which remains constant. And in that scenario, that's the same as saying dh dt equals 0. And that we can get from our equation is negative k square root of h equals 0. Well, we can divide by negative k, so we get 0 equals root h. Only way for that to happen is h equals 0. The only equilibrium where things don't change is when the tank is empty. H equals 0 represents 0 height of water, and any other height, if you have any other height at all, if there's a leak, the water level will change later on. So it makes complete sense that h equals 0 is unequilibrium, and in fact the only equilibrium for this system. Let's look at a more complex model here, the logistic population model, where we have a population rate of change, and it references back to the population itself and a limiting population, which is usually called L, and sometimes it's been called the carrying capacity. So take a look at this differential equation, pause the video again, and consider which population levels P would represent an equilibrium population for this model. All right, then Same process. If we're looking for P in equilibrium, then what we're talking about is P is constant, and that translates to dp dt equals 0. 0 equals negative k times P times L minus P. This is already factored, and so either k equals 0, well, that's not happening. That's a constant that has to do with our proportional growth rate. If it was 0, this whole equation would go away. The more interesting cases are P equals 0 or L minus P equals 0. And these are completely reasonable values. This represents no population. If we have no population to start with, we expect the population to stay quite constant at 0 forever. However, the more interesting case is this case here, which is P equals L. If we start at the limiting population, we're going to stay there forever. And that's why we call that the carrying capacity as well, because if we start at that level, that's exactly how much we can carry in a sustained way. We're going to stay there forever. So we can support that population indefinitely. And that means our right answer here, our correct answer is C.